Hi, everybody. Welcome to the last colloquium, I believe, of the semester. So today, I have the great privilege of introducing Kin Phai Mak here as our colloquium speaker today. So let me just read, so in case I don't remember his CV. So he did his bachelor's at Hong Kong University of Science and Technology. From there, he went to do his PhD at Columbia with, I believe, Tony Hines.
Yes.
Yep. And then he did a postdoc there. After that, he went to Cornell to work at the Kavli Institute, then went to Penn State as a professor, and then went back to Cornell as a professor in 2018, which was actually overlapped with him during my time there as a graduate student. Where, I think I would always be consoled after leaving the office late at night to know that Phai was still there working. Or I don't know what you were doing. Maybe you were just chilling in the office. But right, at least we'd be there together. So since he, he's a, I guess, as you can see from here, he has a joint, at least for now, affiliation with the Max Planck Institute. He, recently, a few years ago, got hired as the director of at the Max Planck Institute, and he's in the process of transitioning over. He is, as you probably know, an expert in all things Moiré, TMD, etc., and is one of the big experimentalists in that field. So I'm really excited to hear what new things he has to tell us today.
Okay, thank you. Thank you very much for the kind introduction and the invitation. Had lots of good discussions with the colleagues here and friends here. And thank you for staying to the last talk or the last colloquium of the semester. I actually just came from Beijing yesterday, so I hope that I'm awake. In my talk, yeah. Okay, so today I'll be telling you about how to use a certain class of material to try to mimic the physics in the Hubbard model, and let's see how it goes. And just feel free to stop me if there's anything unclear or if you have any questions that need clarification. I don't need to finish my talk, so just feel free to interrupt at any point. So before I start, I guess that's the only screen, okay. Before I start, I would like to first acknowledge the people who are actually doing the work I share. Basically, over the years, I collaborate with Professor Ji Shan, Cornell, and the majority of the work actually were carried out by graduate student Yu Xia and a postdoc in my group at Zhongdong Han. And I will also be talking a little bit about earlier results from Yang Xu and Yan Hao Tang, who are now professors in China. And there are two other graduate students who contributed to the works that I'm going to tell you, Yichi Zhang and Raymond Zhu. And also acknowledge theory support from Alan McDonald and Vi Elsa. The TMD crystals are actually from Jim Hong's group. And the boron nitride crystals, for those people who are in the business, they know you guys will know that this is from the famous Japanese group. These two gentlemen here who provided boron nitride crystals to many two-dimensional laboratories. And this is the funding sources. Okay, so I will start with something simple. I thought it's a colloquium, so we start with solid-state physics 101. The type binding model on a square lattice, basically there's only one term in the Hamiltonian that describes the hopping rate of the electrons on a square lattice. And so this hopping term here would then broaden the atomic levels into a band, which is plotted in this Brillouin zone here. So for a half-field, for an occupancy on average with one electron per atomic site here, that corresponds to a half-field band on a square lattice, then the system is actually metallic, right? So there's no gap for excitation. It's a metal system. It's a metallic system. If you put on average 2 electrons per site, then you fully fill this band, and then you will have an energy gap for excitation, and it becomes an insulator, okay? So that's very simple. The bandwidth here is proportional to this hopping rate T here. So that's very simple, but surprisingly, this simple type binding model actually works for about half of the periodic table. It's more about the top half of the periodic table. It works reasonably well. for example, the simple metals, the insulators and semiconductors. On the other hand, it actually fails for about the other half of the periodic table, usually at the lower bottom of the periodic table, where actually the materials display lots of interesting correlated phenomena such as superconductivity, magnetism, and correlated insulators that I will tell you a little bit more about. These are insulators that you would not expect from a band theory. Band theory would tell you that they should be metals, but what experimentalists observe is that they actually are insulators. So to actually try to capture the other half of the periodic table, roughly speaking, in 1963, three gentlemen, Hubbard, Cornell, and Gus Wheeler, independently came up with something now today known as the Hubbard model. It's actually a very simple attempt to try to capture the effect of electron-electron interactions for particles on a lattice. Okay, so what they did is actually really add one more term to the Hamiltonian that describes the on-site Coulomb repulsion if the electron, there are two electrons on the same site. There is a Coulomb energy penalty U here that describes the repulsive energy cost for the electrons. Okay, so of course this actually does not really capture the interaction in real solids, because in real solids the electrons interact with a long-range Coulomb interaction, but nevertheless it's just really a simple attempt to try to describe the effect of Coulomb interaction for electrons. So it turns out that actually even just adding one more term here would give rise to lots of interesting things, and people don't really know how to solve this model. The reason is the following. The T term, because these two terms actually tell the electrons to do opposite thing. The T term would actually tell the electrons to gain more energy by delocalization, then you gain more kinetic energy. And in a sense, it's really telling the electrons to behave more wave-like, right? And on the other hand, actually, the U term here would actually tell the electrons to localize more, because if the electrons move around, and there is actually a higher chance for two electrons to meet on the same site, and that causes Coulomb energy. So this term actually would tell the electrons to behave more particle-like in a sense. So it's really just these two terms kind of tell the electrons to give the electrons conflicting instructions that gives rise to lots of interesting physics. And because there are only two terms in this Hamiltonian, then the physics is really controlled by the ratio of the two terms. It's either U over T or U over W. W is the bandwidth of the system. For a square lattice, the bandwidth is A times the hopping rate T. Okay. All right. Well, actually, even with just these two terms in the Hamiltonian, lots of interesting phenomena can arise. For instance, the phase diagrams, the complex phase diagram of high-temperature superconductors, I will explain a little bit more later. Magnetism, correlated insulators, metal-insulator transition, or Mott transition, and as well as other quantum phase transitions that can actually come out of this this Hamiltonian, which look very simple. Well, of course, there's actually a problem. The Hamiltonian is kind of deceptively simple. It's actually very difficult to solve, and in fact, there's no exact solution in 2D or 3D. So it would be very nice to use some physical system to try to mimic this Hubbard model and try to measure it and try to get the phase diagram and then see whether we can learn something from this physical system that can mimic the Hubbard model. So one of the very famous systems that can mimic the Hubbard model is built on these cold atoms. What they usually do is that they shine laser light to create an optical lattice that they can trap the atoms in this lattice. They can tune the interaction strength. They can tune the hopping rate. And so that's actually a precise Hubbard model simulator. And I'm going to tell you another material system, which is actually less precise compared to the AMO system, but it's closer to a material. It's actually, in fact, it's sitting somewhere in between a real atomic solids and AMO system. So you have a better tunability compared to conventional materials, but it's less precise compared to the AMO system. But I will tell you that actually that indeed the system can behave like a Hubbard model. Okay. So the building block of this material is a monolayer. Is this so-called transition metal dichalcogenic TMD semiconductor. This is actually one layer of such material. And if you look from top down, it has a honeycomb lattice structure like this, which actually looks similar to graphene, except that the A and the B sublattice sites are now occupied by different atoms, so the immersion symmetry is broken. This is the Brillouin zone. Actually, the electronic states of interest are not located at the center of the Brillouin zone. Rather, it's actually located near the corners of the Brillouin zone. So it's located at the K and the K prime. And that's also pretty similar to graphene. Because of the broken immersion symmetry here, you don't have a Dirac point at the K and the K prime valley. Instead, you actually have an energy gap opened at the K and the K prime valley. So these are just two copies of semiconductors, one copy at the K point, one copy at the K prime point, right? And these 2 points are connected by time reversal symmetry operation. And one thing I also want to mention is actually that because of the heavy transition metal atoms in the material, there is a large spin-orbit interaction in the system. And the spin-orbit field is actually pointing in the outer plane direction that locks the spin to the outer plane direction. So effectively speaking, it's like an Ising spin system. The SZ is a good quantum number, okay? The effect of the spin-orbit interaction is to produce a spin splitting at finite momentum. And you can actually see that there's a spin down, spin up splitting here. That would change to spin up and spin down splitting here because the two are connected by time reversal. So down was flipped to up here. And the spin-orbit interaction is kind of important to the story that I'm going to tell you because that removes the spin value degeneracy. So there's actually no more degeneracy in the system. If you think of the Fermi level located in this topmost valence band here, there's only two-fold spin degeneracy left in the system. So for the pristine material, the Fermi level is located inside this big energy gap. The gap size is about 1 to 2 eV. So we are talking about a very large energy scale for the pristine material. Okay, so similar to the famous twisted bilayer graphene, you can use these materials to build Moiré systems or Moiré superlattice. One way to do it is to give it a twist angle for the same layer of material. We call it a homobilayer system. So you give it a twist angle, then you will produce a superlattice structure like this. And the emergent Moiré length scale, A sub m here, is roughly given by the lattice constant of the original material. This is in the angstrom level, divided by theta. Theta is the twist angle measured in radian. Okay, so usually theta is a very small number, so that's why the Moiré wavelength is much bigger compared to the atomic length scale. And typically, we are talking about a length scale about 10 nanometer. So you can think of them as very big atoms with the atomic size about 10 nanometer. There's another way to build a Moiré system using these materials. Is actually, you don't need a twist angle in this case. You can use two different materials. They have a lattice mismatch delta here. Even with 0 degree twist, you actually can automatically get a superlattice structure. And the Moiré period now is given by A divided by delta for the lattice mismatch. And in this particular pair of combination, the lattice mismatch is about 4%, and that would give rise to an 8 nanometer Moiré period in this particular material. Okay. And the Moiré lattice is actually real, and you can directly see them in a transmission electron microscope. This is a work done in collaboration with Dave Mueller's group at Cornell. And you can actually see that the small dots here, the small dots here are the real atoms, but on top of that, you actually can see a Moiré superlattice structure coming out because of the lattice mismatch in these two different materials. In this case, it's actually a 7% lattice mismatch, and that gives rise to a 5 nanometer Moiré period, even you don't have any twist angle in the system. Okay. So now I want to highlight a few interesting features with the emergence of the Moiré length scale. The first is actually the Bloch theorem still holds, and that gives rise to a set of Moiré bands in the mini-Brillouin zone. And that's actually not immediately clear from the structure, from the Moiré superlattice structure here, because strictly speaking, the system is not periodic, okay? But in this limit that the theta and delta here is very small compared to 1, the Moiré length scale is actually much larger than the atomic length scale. In this limit here, actually, you can almost forget about the original lattice length scale. You can forget about A here. You can actually forget that the material is made of atoms. Instead, you just treat the electrons with a certain band mass, move in a smooth periodic potential in this limit. Then what it does is actually to introduce extra Bragg reflection from the superlattice structure. Then you will reduce the band structure in the big Brillouin zone now to a mini-Brillouin zone defined by the Moiré period, and you get a series of flat bands due to the anti-crossing feature of the bands. Okay, so you get a series of flat bands here. The dashed line is the Fermi level. Okay. The second feature I want to briefly highlight is that it's a controllable quantum system because of the longer length scale. Actually, to a pretty good approximation for the semiconductor Moiré materials, you can think of the Moiré potential as a lattice. It's an array of a trapped potential that can trap electrons. So you can think of it as an array of artificial atoms. The trapping depth is about 100 to 200 milli-electron volt. The length scale is about 10 nanometer, much, much bigger than the angstrom scale. So because of the much bigger atomic size, we have a much lower atomic density. In fact, it's only about 0.1% of the real atomic density in the system. And that turns out to be actually significant because with simple electrostatic gating that I'm going to tell you later, you can easily move the Fermi level through multiple of these bands, okay, in the system. That means actually you can put many, many electrons, multiple electrons on average per Moiré atoms inside this system with just one sample and electrostatic gating. And well, in terms of making connection to really like solid state chemistry, every time you move the Fermi level through the entire flat band, that corresponds to actually move the elements horizontally in the periodic table by 2 units in a sense. So it's actually a very tunable system without doing actual chemistry to change or to modify the properties of the material. And finally, the system is strongly correlated. Okay. Now going back to this picture, the electrons trapped in this artificial atom can hop with between the nearest neighbor sites with an amplitude T, and there is a Coulomb repulsion U for 2 electrons on the same site. So already it starts to look like a Hubbard model. And to give you a sense of the energy scale of the system, T is the kinetic energy of the electron. For massive electrons, you just use the typical energy to estimate P squared over 2m. And so that's actually proportional to 1 over the Moiré length scale squared. And that has a T of 1 to 10 milli-electron volt. The bandwidth is actually about 10 to 100 milli-electron volt. You basically multiply this number by about a factor of 10. For the on-site Coulomb potential, we just used the Coulomb form to estimate the magnitude of the U here. It's proportional to 1 over the Moiré length scale. It's about 100 milli-electron volt. So if you divide the ratio U over T here, you find that it's actually proportional to the mass of the electron, and it's also proportional to the Moiré length scale. So longer the Moiré length scale or smaller the twist angle, the stronger the interaction effect is, right? The larger the U over T ratio is. It sounds a little bit weird at the beginning that you make the length scale longer. You seem to actually reduce the Coulomb repulsion energy by making the length scale longer, but the interaction effect actually gets stronger. It's just because the kinetic energy actually decreases even faster with increasing Moiré length scale. Yeah.
How do you know the trapping energy scale? How do you know it's 100 to 200 MeV for is that experimentally determined or?
Yeah. So there are first principle calculations, I would say, that provides an estimate of this how deep the potential is. So for the heterobilayer, what it does is really that there's a lattice relaxation, and there's a deformation potential when you have some periodic modulated strain, and that you will have an energy landscape, right, for that, and that can be calculated from the DFT, but not for a very large period, right? So that gives some calibration for it, yeah. So this is the outline of my talk. I will tell you 2 stories. One is in the limit of very strong interaction, that the kinetic energy of the electron is not very important. Then we get I will tell you stories of Mott insulators and Wigner crystals. And then we are going to tune the system to give it more kinetic energy, and that actually promotes superconductivity. And I'll tell you that how we can use this system to mimic the phase diagram of high temperature superconductors, in particular the cuprates. Okay, so first let me tell you a bit more about this heterobilayer system. the heterobilayer turns out to be the simplest possible Moiré materials that you can think of. It's so simple. It's simple because actually we are talking about two different layers here, and there's a big energy offset between the bands of the two layers. So you don't actually need to really worry about the crosstalk between the different electronic states of the two layers. And so you can actually really talk about the Moiré flat bands of one layer. For instance, you can talk about the Moiré flat bands of the tungsten selenide layer. You can also talk about the Moiré flat bands of the tungsten sulfide layer. So this is very simple. There's no crosstalk of the bands from the two layers. And the spin orbit also removes this valley degeneracy, so you only have really just one spin. You only have two-fold spin degeneracy for each of this flat band in the system. Okay, so it's shown by this 2018 PRL paper by Wu and McDonald that if you just consider the low energy physics of this isolated topmost Moiré valence band in this system, the low energy physics of just this band can be mapped to a Hubbard model on a triangular lattice with a T term of the nearest neighbor and a U term for the on-site Coulomb repulsion. Okay, so this is the simplest possible Hamiltonian for the Moiré materials. Okay, so and when this field just started around 2020, we actually did not really know how to make good electrical contacts to the material. So by the time we invented the different methods to probe the system, so now let me just walk you through a little bit about this method, how we can use optics to probe the electronic states of this system. So we call it the exciton sensing or the Rydberg sensing technique. Let me just walk you through how it works. We start with this monolayer semiconductor. We shine light onto the material, and the light would just generate the electron and hole pair because we are exciting an electron from the valence band to the conduction band and leave a hole in the valence band. Okay? The electron hole pair, they bind together with the Coulomb attraction. These are the Coulomb field lines. And you can just think of it as like a two-dimensional hydrogen atom living in a two-dimensional plane with a 1/r potential. Then the binding energy is proportional to 1/epsilon squared. Epsilon is actually the dielectric constant of the surrounding substrate. Okay. You can measure the binding energy by doing optical absorption spectroscopy on this monolayer semiconductor. This is a schematic plot. This is absorbance as a function of the photon energy. You can see the 1s Rydberg state, 2s, 3s, 4s, and so on and so forth. These just are like the Rydberg states of the hydrogen atom, but in two dimensions, until you hit the band edge here, and that's actually the band gap of the material without Coulomb attraction. So the energy difference between this 1s Rydberg state and the band gap, that gives rise to the binding energy of the excitons. Okay? And how we can actually use this exciton binding energy as a probe of the physics of a sample. Now imagine you put a sample very close to this monolayer semiconductor, which acts as a sensor, but not touching the sensor, okay? So if the sample is metallic, that means that you have a large negative dielectric constants in the environment, and that actually effectively screen out the Coulomb attraction between the electron and holes, and that will reduce the binding energy, so you would get a smaller binding energy in the system. If the sample is insulating, and the dielectric constant will be smaller, and as a result, you get a larger binding energy in the system. So by just measuring the binding energy of the excitons, not on the sample, but in a remote sensing layer, you will be able to tell whether the sample is in some incompressible state or compressible state. So to make this experiment work, we built this structure. This is the work of Yang Xu a few years back. So we have a sample here. The sample is some Moiré system. I'm going to first tell you an example of a very large U/T. And then there is a sensor here, which is this monolayer of semiconductor. We shine light to excite electron hole pairs in this sensor. And the sensor and the sample are separated by a very thin boron nitride. The boron nitride is a very good insulator. It's very thin such that the Coulomb field lines of this electron hole pair can penetrate through the sample so that it can act as a sensor to see what's happening inside. And then we have the top gates and the bottom gates. The function of the two gates basically is to keep the sensor completely charge neutral and also to tune the doping density or the electron density continuously in the sample. Okay, so that's the experiment. And this is the result. I'm just going to spend a little bit of time on explaining this result here. This is the photon energy that we basically is our photon energy. We probe the sensor, and you can see these resonances here. This is nothing but just the 2s Rydberg states on the sensor, not on the sample. And this axis is the gate voltage that tunes the electron density in the sample. And positive gate voltage means electron doping. Negative gate voltage means hole doping. Filling factor 1 here means 1 electron per Moiré site, so that corresponds to half band filling. Filling factor 2 means 2 electrons per Moiré site, that corresponds to full band filling. All right. Negative means for holes. Right. So immediately, by just looking at this, you actually can see that there is a strong resonance at 1, filling factor 1 and filling factor 2, -1 and -2 here. And this strong resonance, which is blue shifted from the background, that actually means a larger binding energy for the excitons. So these are actually insulating states. So this background means metallic states. Each of this big resonance here means an insulating state. Okay. All right, so what are these insulators? The filling factor 2 insulator is actually kind of trivial because that corresponds to a fully filled band. So that's really just an insulator from Pauli exclusion, and that's just a band insulator. And these 2 electrons per Moiré site, they just form a spin singlet because of Pauli exclusion. The filling factor 1 insulating state is actually more interesting because for band theory, filling factor 1 means a half-filled band. Now we only have one band system. Without any interaction, that would just tell you that it should be a good metallic state. But because of the strong Coulomb interaction, now a Coulomb gap is open at the Fermi level, and you just get an insulator because of the strong Coulomb repulsion. In fact, the Coulomb repulsion just locks the electrons on the lattice sides because if the electrons move around, then they meet each other on the same side that causes Coulomb repulsion energy, right? So this is known as a Mott insulator, which the band theory would tell you it should be a metal. So to actually show that it's really a Mott insulator, go back to this picture here. The Mott insulator and the band insulator, both that the charges are localized. But in the Mott insulator, you actually can see that each of these localized electrons carries a spin in the system. So to really show that it's a Mott insulator, you need to measure the spin susceptibility. Right? In particular, you want to show that there is an emergence of local magnetic moments in the Mott insulator. So this is the work by Yan-Hao Tang a few years back also. What we're measuring here is the temperature dependence of the magnetic susceptibilities for the Mott insulating state. And if you have a lattice of local moments here, then the magnetic susceptibility will follow something called the Curie-Weiss law. And the black dots are the data points, and the red curve is a fitting using the Curie-Weiss law. And from the fitting here, we can also extract the Curie-Weiss temperature, which is actually proportional to the exchange interaction between the local moments. And the exchange interaction is about -1 Kelvin. And the negative sign actually tells you there is antiferromagnetic interaction between the local magnetic moments. And that's consistent with the super exchange mechanism due to Anderson's work. Okay. And this energy scale, of course, is very small because the spins are actually apart from each other by 10 nanometer. So compared to the atomic scale material, this is a very small energy scale. Okay, so going back to this picture very briefly, in addition to seeing this insulating state at filling factor 1, filling factor 2, you can also see that there are lots of insulating states at fractional filling factors. For instance, 1/3, 2/3, 1/2, 6/7, and something like that, right? And what are these? These are actually the charge order states. They are also insulators. These insulating states actually arise because of the longer range Coulomb interaction for the electrons. And so to save the Coulomb repulsion, the electrons will self-organize into these periodic patterns that break the translational symmetry of the original lattice. For instance, the 1/3 state, well, let's say the 2/3 state would form a honeycomb lattice on the triangular lattice, and the 1/2 state would actually form a stripe face that spontaneously break the rotational symmetry. The same for the 2/5 state. This is kind of interesting. The electrons would pair up and then form this kind of a charge order, a stripy pattern here. So this breaks rotational symmetry, which we can also verify by optical birefringence experiments. Okay, so that's the conclusion of this part. What I've been telling you here is that in a heterobilayer Moiré system, with very large U over W ratio, where the kinetic energy of the electron is not very important, then we are dealing with a system with very flat bands. The electrons are essentially classical. It's a kind of interesting system to explore Mott insulators and Wigner crystals, and you can see magnetic moments. But it's not very good for superconductivity because the electrons are so classical that superconductivity is really a macroscopic quantum phenomena. We would like to actually increase the kinetic energy of the system, and hopefully we can get superconductivity here. So our goal is actually to reduce that's my second half of the talk, we would like to reduce the U over W ratio or the U over T ratio here. So I can stop for 10 seconds or something. Questions?
Large spin orbit coupling. How do you know that the hopping parameters are all real? Why do you not have something like a Haldane model?
Yeah, actually, that's a very good question. But for a heterobilayer system, the bands are very far apart from each layer. Then you only have just really one band system and spin degenerate. You can only get you cannot get trend bands in that system. So for a homobilayer system, which you can actually get interlayer hopping, and in that case, it's actually not just a spin degenerate, but it's also layer degenerate. In that case, you can get trend bands. Yeah. Okay. Yeah.
Can I ask a question? That just now you showed the map, we can see the integer filling factor like 1 or 2. Because right now the degeneracy here maybe for the single band is 2. So I'm curious whether it's possible to observe maybe 3 or 4.
Yeah, actually, we have done a measurement on a slightly different material system, but also a heterobilayer. You can see filling factor incompressible stay up to filling factor 8. Yeah.
So for this particular, for this is maybe different because this is the single Hubbard model, single band.
Yeah. No, you can still see. You can see actually filling factor 3 and filling factor 4. Yeah. But in a sense, if you keep going to a higher filling factor, and then it starts to become a problem because the trapping potential is only about 200 milli-electron volt deep. So in a sense, if you just fill more electrons, the electronic wave function of the higher field electron will be more spread out, and the kinetic energy becomes very large. Then you will lose the incompressible states eventually. Yeah. So you need, in order to see many states, you need a system with very deep trapping potential. And some of the materials can be really deep trapping potential. Okay, so I'll give a very brief introduction to cuprate high TC superconductivity that's discovered experimentally in 1986 by Bednos and Müller, and they quickly received the Nobel Prize a year later. And this is the phase diagram. Well, so the high TC cuprates is actually interesting, not just because of the very high TC, but also because of the very complicated phase diagram. So let me walk you through this phase diagram a little bit. A zero filling here, that corresponds to actually our filling factor 1. That corresponds to a Mott insulator, in particular antiferromagnetic Mott insulator on a square lattice. And with doping, you quickly kill the antiferromagnetism, and then the superconducting dome arises once you kill the antiferromagnetism. Very high doping away from the Mott insulator, then everything actually turns to be more normal if you get a normal Fermi liquid at these very high doping levels. And there are two things I want to briefly mention. There's a pseudo-gap phase here that the system is metallic, but there is a spectral gap, which can be seen in RPAS or in spin susceptibility measurements. And there's another phase actually above the dome that even with less understanding of what's going on, it's called a strange metal, that it exhibits a T-linear resistivity. That it seems from a phenomenology point of view, it just doesn't behave like a usual Fermi liquid. So that's why people call it a strange metal or a non-Fermi liquid. All right. So very soon after the experimental discovery, Anderson in this paper here in 1987 already pointed out that the effect of strong correlation is really the root for the emergence of high-temperature superconductivity. In particular, he proposed that the Hubbard model really can capture the essential physics of this phase diagram here. Okay. And his idea is actually connected to the concept of a Mott transition. And let me tell you briefly what the Mott transition is. We already talked about the Hubbard model. in the limit that U is very small compared to the bandwidth, for a half-filled system, and the system will be just a metal, as I told you about. And if for U very large to W, I already told you that it's actually a Mott insulator. A Coulomb gap is opened at the Fermi level, and the Coulomb gap for in this limit is about U here. And the system is actually an antiferromagnetic Mott insulator on a square lattice. So Mott's idea in 1961 is that if you imagine that you can tune continuously either the interaction or the bandwidth of your system, let's say you can continuously tune the bandwidth of your system, when the bandwidth becomes comparable to the U here, then there should be a sudden metal to insulator transition. And that's Mott's idea. This is called the bandwidth-tuned Mott transition. And Anderson's idea is actually that the high TC phenomenology should appear around this Mott transition, okay? And so we would like to actually have a system that can allow us to tune to the intermediate U over W near this Mott transition here, that let's see whether we can actually get the phenomenology of high TC. So in order to do that, we actually now go to a homobilayer system. And one advantage of the homobilayer system is actually, you look at this ratio of U over T, it's proportional to the Moiré period. In a homobilayer system, the Moiré period is actually proportional to 1 over theta. Theta is the twist angle. So we can continuously tune the Moiré period in a homobilayer, at least more easily compared to a heterobilayer. So that's the idea that we hope to be able to use the twist angle to tune this U over T ratio continuously, okay? And now let me walk you through the band structure of the homobilayer a little bit, which actually is a little bit different compared to the heterobilayer. This is the topmost Moiré valence band of a twisted homobilayer tungsten selenide, energy versus momentum in the Brillouin zone. And you see this topmost spin degenerate band in the system. So that's with no displacement field, meaning that the two layers, we did not apply any vertical electric field to the layers, and the two layers are at the same electrostatic potential. You can apply a vertical electric field to the two layers, then the two layers are at a different electrostatic potential. Then the band structure becomes something like this. It's kind of interesting because now you can actually see that at finite momentum, there's a spin splitting emerge because of the applied electric field. So in a sense, the electric field is actually producing a spin-orbit interaction in the system. So this series of, I'm not going to get into the details, this series of theory work actually showed that the low energy physics of this topmost Moiré valence band, including the displacement field, can be mapped to a modified triangular lattice Hubbard model. You still get the T term, you still get the U term here, but there's an extra phi term in the system, and phi will be 0 for 0 displacement field, so that's actually going back to the usual Hubbard model on a triangular lattice. But if you apply a displacement field, that phi will become finite. And that actually, this is the spin orbit term that accounts for the spin splitting due to the displacement field. So the electric field actually tunes both the spin orbit interaction as well as the band structure, in the sense the band structure of the system, okay, in this homobilayer. So it actually has an extra tuning knob compared to the heterobilayer, which is the electric field. So in our experiments, this is the work of these two gentlemen here, and we put the preprint on the archive. In the actual experiments, we built a homobilayer device encapsulated between the top and the bottom gates. And we contact the device with multiple electrodes now. You can measure the longitudinal and the Hall resistances. And the two gates actually allow you two tuning parameters, both the doping density in the Moiré sample and also the vertical displacement field that tunes the band structure of the Moiré sample. So in our experiment, we cos-tune the U over W ratio by the twist angle. So the twist angle provides the cos tuning of the kinetic energy of the electron. The fine-tuning is by a displacement field on a particular sample. So in order to fine-tune this ratio, we further apply a vertical displacement field using these two gates. Okay, so this is our experiments. So without getting into the understanding, let me just first show you the results, then I'm going to explain the two limits of small u over t and the large u over t. So what I'm plotting here is the resistivity of the sample as a function of the doping density, which is the x-axis here, converted into the filling factor Again, our convention is that filling factor 1 is 1 hole per Moiré unit cell, so that corresponds to half band filling. And this is the displacement field axis, which tunes the band structure of the homo bilayer. And from left to right is increasing twist angle from 2.1 degree to 4.7 degree. On this side is small u over w. On this side is large u over w ratio. Okay, so now you can actually see that there's no more insulating state. Everything is metallic in this large twist angle sample. On the other hand, for small twist angle sample like here, the half band filling is basically dominated by a more insulating state. Well, red here is actually a really large resistance, right? It's in log scale. So red here is an insulating state at half band filling. So you can see that the general trend is that the more insulator weakens with increasing twist angle, which is expected because you tune the you decrease the U over W ratio. And another interesting observation is that this blue region basically has zero resistance. These are the superconducting states. It follows the location where the more insulator is destroyed. Okay, so I will come back to that point later. So now let me explain how to understand this kind of phase diagram. And let me just start with something very simple. Go to the large twist angle with a small U over W ratio, where the Coulomb interaction is less important. And you don't have a more insulator here. Okay, so this is the data. On the right-hand side, I'm showing the expected phase diagram from band structure calculations. This, again, is doping density. This is displacement field. The phase diagram can be separated into 3 regions. One is actually this small density and large electric field region. And what it does is basically that the electric field will polarize the holes either to the top layer or to the bottom layer, right? So basically, this we call the layer polarized region. And in this region here, the physics is actually not that different from a monolayer semiconductor. So that's kind of boring. So this layer polarized region is kind of boring. The more interesting region is here, that in the higher doping density region, in a smaller displacement field. Here, you really get the charge carriers are shared between the 2 layers, and we call it the layer hybridized region, where the Moiré effect is really important. And these are the phase boundary between these regions. And the dashed line is actually the expected location of the Van Hove singularity from band structure calculation. Remember that our displacement field is tuning the band structure, so that's why the location of the Van Hove singularity can be moved by the displacement field. Okay, so now you look at this and you compare to the experimental data, you can clearly see that there's this phase boundary that separates the layer polarized and the layer hybridized region. And you also can see that there is a local resistivity maximum here, and that corresponds to the location of the Van Hove singularity, because when you have the Van Hove singularity, you have a higher resistivity automatically. Okay. And of course, you also actually can see that there's superconductivity coming out when the Van Hove singularity hits near half band filling, and the result is actually similar to the result published earlier by the Columbia group earlier this year on the 5-degree twist angle. So basically, for anything beyond 4.7 degree twist angle, band structure works reasonably well, except that you get superconducting states around here. Okay. So now let's go to actually a smaller twist angle sample with this picture here. Let's go to a smaller twist angle sample with large U over W ratio. And this is basically the data. You can still see the layer polarized region and the layer hybridized region. But in this small twist angle sample with large U over W ratio, you can actually see that at half band filling, the phase diagram is dominated by a Mott insulator at half band filling. So band theory completely fails near half band filling. The Mott insulator exists over a wide range of displacement field, and then superconductivity actually comes out. This is the superconducting state. It comes out directly from the Mott insulator tuned by the displacement field. So we can actually zoom into this region here. This is the data zoom in. You can actually see that by just tuning the band structure using the electric field, you can go directly from a superconductor to an insulator. These are some line cuts. You can actually see that this is a diverging resistivity with decreasing temperature. That's an insulator. And then you tune the displacement field a little bit, it goes to a superconductor that the resistivity drops to 0. Okay. So now let's actually go back to this data with different twist angle. I explained these 2 limits here to you. Now actually you can actually sort of see that with increasing twist angle, we systematically decrease the U over W ratio. the Mach insulating state just systematically weakens with increasing twist angle. But interestingly, you can actually see that the superconducting state, which is the blue areas here, it does not really follow the location of the Van Hove singularity, which is actually this dashed line, but rather it follows the location of the Mach transition, right? It just appears right next to the point that the Mach insulator is killed by the displacement field or by the twist angle. Okay, so now I just, for the remaining 10 minutes or something, I'll just tell you the last bit of this. Let's just go to this intermediate U over W ratio in this twist angle that the Mach insulator is barely killed by the twist angle. And then let's look to see whether there is some kind of high TC phenomenology can come out. So this is a zoom-in plot of one of these islands here. And you can actually see the Mach insulator wrapped around by the superconducting dome. When you dope very far away, it becomes just the Fermi liquid, okay? And you can actually, let me just show you some transitions, and you can actually see that there's a superconducting transition at about 400 millikelvin, and then the resistivity goes to 0. You apply some small out-of-plane magnetic field, you kill the superconducting states. You can extract some parameters. The coherence length is about 34 nanometer. The Moiré period is about 4 nanometer. So the ratio of the coherence length to the Moiré period is about a factor of 8. So that already shows it's kind of a tightly bound Cooper pairs because the Cooper pair size is only about a few times of the lattice scale. And the mean-free path is about 400 nanometer. It's about a factor of, more than a factor of 10 of the Moiré period. So the superconductor is also very clean. Okay, so now with this, let me just walk you through the phase diagram with just one line cut, then I'm going to wrap up. So let's just fix the electric field here. Remember, the electric field provides fine-tuning of the band structure. And I'm just going to fix at this particular electric field with a fixed band structure, and I'm going to examine the temperature dependence phase diagram of the system. So this looks something like this. This is the doping density. Filling factor 1 is the correlated insulator. This is temperature axis. You can actually see that when the system cools below about 3.5 K, it goes from a metal to an insulating state, like this. And you can also see two boundaries of the doped Mach insulator here and there. And actually, this is the Hall resistance map. And you can actually see that once the insulating state sets in, you dope a little bit away from the insulating state, you get a large Hall response. That would mean a small Fermi surface. So on this side is actually a small electron Fermi surface. On this side is actually a small hole Fermi surface. When you immediately dope the Mach insulator, only when you dope very far away from the Mach insulator, you recover the band Fermi surface. And then when you kill these small Fermi surface metals, and you get the superconducting domes coming out. So it starts to look like a little bit like the high TC phase diagram. And let me just walk you through a little bit to really show that it indeed looks like the high TC. For instance, we look at the temperature dependence. We draw one line cut at fixed half band filling. This is, you can actually see a metal to insulator transition at about 3K, and then the magnetic ordering at a slightly lower temperature. Okay, and to show that there's indeed magnetic ordering, we measure, the theory would just tell you that you expect it to be a 120-degree new order for XY model. So to show that it's indeed an antiferromagnetic Mach insulator, we measure the magnetic susceptibility as a function of temperature. And you actually can see the Curie-Weiss behavior, and then you see a bump near the ordering temperature. Below the ordering temperature, the magnetic susceptibility decreases. You can fit it, and you can actually extract it has a negative Curie-Weiss temperature. So I hope I can convince you that it is indeed an antiferromagnetic insulator. You can dope it very far away from the Mach insulator. So I'm taking a cut here, about 13% doping from the Mach insulator. And now everything becomes actually more normal. The resistivity scales with temperature as T square at low temperature part. And it deviates from the T square dependence at this coherence temperature scale, which is proportional to the Fermi temperature. And we can extract this coherence temperature. It actually goes towards 0 in the superconducting dome. And you can do this side, you can also do on this side. So more interesting is actually in the underdoped regime. So that's the overdoped that you get everything normal. In the underdoped regime, the blue curve is the resistivity. You actually can see that there's a bump and a peak near the near temperature. And the red curve is actually showing the Hall density. So at this phase transition here at the near temperature, there's a big reconstruction of the Fermi surface. Actually, the Hall density jumps by a unit of 1, nearly 1. So what that means is actually that the Fermi surface will go from a band structure like Fermi surface, and once you go below the ordering temperature, it jumps into a small Fermi surface that is only determined by the extra doping away from filling factor equal to 1. Okay, so the near temperature at this particular line is about 2.3 Kelvin, and you can extract the near temperature as a function of doping. It goes towards 0 to the superconducting dome. So the superconductivity really comes out when you kill the antiferromagnetism. And if you zoom into this plot here, really try to zoom into this superconducting dome, you also can actually find coexistence of antiferromagnetism and superconductivity. For instance, you can actually see that this this antiferromagnetic dome here overlaps with the superconducting dome. If you make one line cut near here, you can actually see there is a near transition at about 1 Kelvin, and below about 300 milli-K, it develops the superconductivity. So what this plot shows is actually that the superconductivity can develop from a small Fermi surface antiferromagnetic metal, and that allows us to extract a TC over TF ratio here to be about 3.5%. So that's really, in this sense, it's actually a high TC. So the absolute TC is very low, but the relative TC is very high in this system. Okay, finally, you can also make a knife cut on this above, exactly at the superconducting dome, and you can actually see that after the superconducting transition, about 300 milli-K, there is exact T-linear resistivity spanning at about 2 orders of magnitude in temperature. So it's very good T-linear resistivity, strong deviation from the Fermi liquid picture. So it suggests that the emergence of strange metal in the system. Okay, so this is the extractive phase diagram. Then I'm done here. So you can actually see that starting with the Mach insulator, we dope it, we kill the antiferromagnetism, then you get the superconducting dome. Very high doping density, you get the usual Fermi liquid. And above the superconducting dome, you also get the strange metal behavior with linear T resistivity. At the bottom, I want to highlight one more thing. The red curve is actually the Hall density measured at low temperature. You can actually see there's a Hall density jump by nearly a unit of 1, which is exactly at the superconducting dome. Okay, so this is something also people have seen in the cuprates. There's a reconstruction of the Fermi surface near the superconducting dome. But you can also tune the band structure to access the phase diagram that I'm not going to tell you about. And you can tune the electric field that you can kill the Mach insulator to get a superconductor, etc. So I will skip all of this. So this come to my conclusion. So I hope to convince you that there's indeed high TC phenomenology near the Mach transition, so it really promotes the viewpoint of strong correlation. And the Mach transition in our system is really systematically. You can tune it by the electric field that also fine-tunes the bandwidth, but more importantly is tuned by the twist angle that can cross-tune the bandwidth by a large amount. And the superconductivity really comes just right next to the Mach transition. So I would say that it's pretty difficult to explain the emergence of superconductivity using pure electron-phonon coupling theory, because in that case, your highest TC would follow the location of the Van Hove singularity. But here, the superconductivity always follows the location of the Mach transition. So it really has to come from Hubbard physics or some kind of spin fluctuations near where you kill superconductivity. So I hope that this kind of provides some kind of guidance or picture to the problem of a high TC and its connection to the Hubbard model. So with this, I thank you for your attention.
Hello, check. Yeah, so if anybody has any questions, mic over.
This is really beautiful work. Thank you. Are you surprised by the degree of particle-hole symmetry in your phase diagram? It looks like the strange metal behavior is the main difference between the two doping regimes.
Yeah, actually, so first of all, there's pretty big asymmetry in the phase diagram that on this side of doping, you get the strange metal right above the superconducting dome. On this side, you actually get the strange metal behavior down to the lowest temperature only when you are away from the superconducting dome. Yeah, so that's one thing, it's some kind of asymmetry. And also the degree of asymmetry depends on your band structure. So it depends on basically the vertical displacement field. If you cut the displacement field here, you will only get a dome on one side of the phase diagram, but not on the other side. So I wouldn't say that there is a perfect electron hole symmetry. Rather, it's actually quite asymmetric, I would say, yeah.
Okay, and do you think there's a significant next nearest neighbor hopping amplitude?
Yeah, this part I cannot say. We don't know, at least experimentally, we don't know how significant the next nearest neighbor hopping. But from a theoretical point of view, they calculate the band structure using DFT. Then they fit the DFT band structure using the continuum model, and just including the nearest neighbor T, it's already enough to basically match the band structure. So it seems from a theory point of view, it's not very important, the nearest neighbor.
Thanks.
Yeah. I guess maybe you asked this question is connected to the square lattice. But this is a triangular lattice, actually. In some sense, the square lattice with nearest neighbor hopping is making it a bit more like a triangular lattice. Right? So a triangular lattice, even with the nearest neighbor T, you get a huge amount of frustration already. Yeah.
Thanks for a very, very interesting talk. So I wonder, is it possible to say anything about the nature of pairing in your superconductor?
We cannot say anything about pairing symmetry now. So we want to measure, for instance, the tunneling spectrum. And maybe even better is actually to measure some kind of an angle-dependent Josephson effect to compare, well, maybe it's really measuring the current phase relation to see whether we, maybe there's some kind, actually the theory calculation suggests it's a D plus ID, which breaks time reversal, which is something that actually we can check if whether it breaks time reversal or not. We can do this magneto-optical measurement, but we haven't done it because the TC is pretty low, so we cannot really do it now, but we plan to do it in the future. Yeah, so checking time reversal symmetry breaking is another thing that we should try, yeah.
Thank you for your great talk. So I have a question when you observe the superconductivity under different twist angle, so do you observe the superconductivity survive at a smaller twist angle, maybe nearer 2 degrees, that sometimes people think there's some topological chain insulator maybe?
Yeah, yeah. So for the twisted tungsten selenide, it seems that at zero electric field, we never saw, at least for twist angle larger than 2 degrees, we never saw a churn insulator develop a filling one. In order to induce a churn insulator, we need to apply a small magnetic field for the about 2 degree twist angle. Actually, for the larger twist angle, we never saw any churn insulator. So that's why we believe that at large twist angle, maybe larger than about 4 degrees, the band is not a churn band at all. So it's a flat band, but well, you get the Mott insulator, but you don't get a churn insulator due to interaction. So all this insulator is topologically trivial. Well, it's not trivial, but it's topologically trivial, but it's not a churn insulator. Even you apply the magnetic field to 12 Tesla, you still do not see a churn insulator. You just see Landau levels, you see Landau fans, but you do not see a churn insulator. And that's why we think that a large enough twist angle is not a churn band anymore. A small twist angle, it's actually a churn band. We know that. So that continuum model parameter is twist angle dependent in the twisted tungsten selenide. So going back to your question, if it's very small twist angle here, we believe it's actually that the kinetic energy is too small. We are too far away from a Mott transition, and we just never saw any superconductivity in a small enough twist angle. Yeah.
Thank you for the brilliant talk. I have 2 silly questions. For the first question is that you mentioned that those AMO people, they also simulate the Hubbard model, right? Do they see similar patterns here, like the Mott transition is important, or the coexistence of interferomagnets?
So one thing we can sort of brag about our system is that we can go to a lower effective temperature than the AMO system. So they are more exact Hubbard model simulator. They have more controllability compared to our system. But they have very low temperature, but they actually cannot reach the they cannot reach an effective low temperature. I think, I don't know the record number now. Is it about 10% of T or something, or 20% of T or something? So the lowest temperature they can cool down is a substantial portion of the kinetic energy of the electron. But now here we can actually cool down to a much, much lower energy scale compared to their system. Yeah.
Okay, I see, it's very impressive.
Yeah.
And another question is that I see that the superconducting phase happens at Hole fielding that is actually 1.0. Yeah, and in some later graph, I saw it happen sort of at nu equals 0, like when you're tuning the electric. Right. Oh, I'm sorry. Right. For this graph, it doesn't seem that. Like in the later graph, we have the superconducting dome that happens at 2 places. Right. Like how does this? So for this graph, I don't see the superconducting phase to happen at nu equals 1. Right.
Oh, yeah. So it depends on the electric field, because we are cutting at a particular electric field here.
Oh, I see.
Near the Mach transition. I did not prepare that slide, but if you make a cut here at a larger bandwidth here, then you totally kill the Mach insulator. Then you just have one single superconducting dome.
I see.
Yeah.
I see. But can we say about the TC? Is it like higher or lower?
Actually, the highest TC is really very close to right next to the Mach transition.
I see.
If you are very far, if you go a little bit further away from the Mach transition, all this region have lower TC. You really have the highest TC around here.
I see. Thank you.
Just right next to the insulator. You just get the strongest superconductivity. Yeah.
Thank you.
Any other questions? All right, well, I guess our time is up, so let's thank Kin-Fi for a great talk.
Thank you.
I guess we'll see you all next semester.